In this video we're gonna answer the question, is the sum from n equals 1 to infinity of minus 1 to the n divided by n equal to pi? To answer this, we first are gonna need a theorem. And the theorem says that if we have a sequence and the series of that sequence converges but not absolutely, then for every alpha, a real number, there exists a reordering b sub n of our original sequence a sub n, such that the series of b sub n converges to alpha. We're gonna have a look at the proof. If you don't care about the proof and all you want to know is the answer to this question, then I'm gonna leave the time lapses in the description of the video for you to jump ahead. However, I recommend you look at the proof because it will give us a way to find this reordering b sub n. So to start with the proof, we're gonna create two new sequences. b sub n is going to be formed by all the numbers in our sequence that are greater than or equal to 0. And another sequence, q sub n, that's gonna be formed by all the numbers in our sequence that are smaller than or equal to 0. We know that the sum from n equals 1 to infinity of the absolute value of a sub n is infinity. This series diverges, and the reason for this is that our series converges, but not absolutely. So then, with this, we know that one of the series of p sub n and the series of q sub n does not converge. But in fact, both series diverge. Because if the sum of p sub n had bounded partial sums, and the sum of q sub n had non-bounded partial sums, then the series of a sub n would have non-bounded partial sums, and it would diverge. This is obviously an absurd, because we have as a hypothesis that the series of a sub n converges. So the series of p sub n diverges. What this means is that there exists a natural number n such that the sum from n equals 1 up to n of p sub n is greater to alpha, where alpha is the real number we have from our theorem. So we're gonna call n1 to the smallest of all n's. What this means is that the sum from n equals 1 up to n1 minus 1 of p sub n is smaller than or equal to alpha. But the sum from n equals 1 up to n1 of p sub n is greater to alpha. So we are actually adding just enough positive numbers to be above alpha. Then, if we call S1 to this sum from n equals 1 up to n1 of p sub n, S1 is greater to alpha. And then S1 minus alpha is smaller than or equal to S1 minus the sum from n equals 1 up to n1 minus 1 of p sub n. So in S1 we have all the positive numbers up to n1, and then we are subtracting all the positive numbers up to n1 minus 1, and so we're only left with p and 1. And the idea is to now add negative numbers to have a sum smaller to alpha. So what we're gonna do is choose m1 such that t1, which is going to be s1 plus the sum from n equals 1 up to m1 of negative numbers q sub n is smaller to alpha. So what we first did was add positive numbers so that the sum of those numbers would be greater to alpha. And now to that sum we added negative numbers so that the total sum would be smaller to alpha. And we are gonna continue doing this, obtaining sums that are alternatively greater than and smaller to alpha. So the first sum was S1, it was greater to alpha, and it was equal to the sum from n equals 1 up to n1 of p sub n. Then the following sum was T1, it was smaller to alpha, and it was S1 plus the sum from n equals 1 up to m1 of q sub n. Then we're gonna have S2 greater to alpha, and it's gonna be the sum between T1 and the sum from n equals n1 plus 1 up to n2 of p sub n. Then we're gonna have T sub 2 smaller to alpha, and this one will be S2 plus the sum from n equals m1 plus 1 up to m2 of negative numbers. And so by doing this, what we are obtaining is that our sequence b sub n will be equal to, first we have n1 positive numbers, so we have p1, p2 and so on, p sub n1. Then we have negative numbers from q1, q2 up to qm1. Then again positives, p n1 plus 1, p n1 plus 2 up to p n2. Then again negative numbers, q m1 plus 1 up to q m2, and so on. We continue like this indefinitely. And the partial sums of p sub n will be, first we add all these numbers up, these are all positive numbers, and as a result we have S1. Then we have all these numbers, these are all negative numbers, and the sum of these two will give us T1. Then we have again all these positive numbers, and when we add those positive numbers to T1 we have S2, and then again negative numbers, and the sum of all this is T sub 2. So what we're doing is, if this is alpha, we are starting with positive numbers until the sum is greater to alpha. Once we have something above alpha, we start subtracting until we are below, and then we add numbers again, and so we continue. And it is clear that this series will converge to alpha. We know that S sub k, so the k time we add positive numbers minus alpha, will be always smaller to p sub nk, and t sub k minus alpha will be smaller to negative, because q's are all negative numbers, so it's minus q is a positive number, sub mk. But both pnk and qmk are terms from a sub n, and because the series of a sub n converges, then a sub n goes towards 0. So then p sub nk goes to 0 and q sub mk goes to 0. So s sub k minus alpha goes to 0, and t sub k minus alpha goes to 0, and thus both s of k and t sub k are partial sums of p sub n, then the series of p sub n converges to alpha. So now that we have proven this theorem, we can actually answer the question: is the sum from n equals 1 to infinity of minus 1 to the n over n equal to alpha? Well, this is a series that converges, but it is not absolutely convergent. So we can use this theorem with alpha equal to pi and conclude that it does converge. But to do so, we have to find b sub n. And we're gonna do this with the computer. We're gonna start by setting the format to long, because we're working with long decimals. Let's first do the script for positive numbers. We create a function that will give us two values, n and the total sum. And it's gonna have three arguments: start sum, end sum, and previous sum. We start by setting the positive sum equal to the previous sum. And now we move n from the start sum up to the end sum, moving on each step only one unit. And we check if the modulus between n and 2 is equal to 0, to check if the position of m is odd or even. So when it is 0, we add to the sum 1 over n. And now we have to check if the sum is greater to pi. If it is, we have finished. And when we get to the extreme of the n, we get to the end sum, then we make the end sum bigger and run our function again. So now we have finished the function and we can test it for the first number n1. So we'll save these numbers in a variable n1 and s1. We're gonna use as a start sum value the number 1, as end value the numbers 605, and the previous sum is equal to 0, because we've made no calculations. So now we run the script, and we get that n1 is equal to 602, and s1 is 3.14 something, greater to pi. Now we have to create a script for the negatives, and it is very similar to the positives, so let's just copy and modify it. We change all the n's for m, post sum is gonna be neg sum, the name of our function is gonna be sum negatives. Now we have to check if the numbers are odd, and if they are, subtract 1 over m. And we also want the sum to be smaller to pi. Now that we've finished, we can run the script to find the first number m1. We save these values in the variable m1 and t1. They're gonna be the sum of negatives, starting from 1 up to, let's say, for example, 4, and with the sum starting at s1. If you remember, t1 was the sum of s1 plus some negative numbers. So when we run the script, we get that m1 is equal to 1 and t1 is 2.14. 2.14 is smaller to pi, and this makes sense because in our series the first negative number was minus 1. Let's continue by finding the second positive. n2 and s2 are gonna be the sum of positives, starting from n1 plus 1, finishing at, for example, 800, and starting now with t1. t1 was the result from the previous calculation. Running the script gives us 4,444, and this 2 that's greater to pi. And now we find m2 and t2. We're gonna start the sum at m1 plus 1, finish at, for example, 9, and start the sum with s2. When we run the script, we get that m2 is equal to 3, and t2 is 2.8, that's smaller to pi. We can continue doing this infinitely many times to find the reordering b sub n of a sub n. I will leave a link for the download of this script, so you can also find it in the Patreon page, also that will be free for all, and in the Discord server. Let's now go to the board and write all these things down. So what we just did in the code was find the numbers n1, m1, n2, and m2, and we could have continued with this process indefinitely. So our series, the first term of it are minus 1 plus 1/2 minus 1/3 plus 1/4, and so on. We can continue. We have these positive numbers that are all the numbers in p sub n, and the negative numbers that are part of q sub n. So in the first step, we calculated S1. We said it was the sum from n equals 1 up to n1 of p sub n. And the program gave us n1 equals to 602. But when we check how we defined p sub n and how we defined the indexes in the program, we see that in the program we're actually counting this as the first index, this one as the second one, the third one, and so on. But the sub-indexes of p sub n are, this one is the first one, this is the second one, and this is the third one. So when we got n equals to 602, we actually got n equals to 301. So our sum is from n equals 1 up to 301 of p sub n. So we are actually adding a lot of numbers here. We have 1/2 plus 1/4 plus, and so on, 301 times. So the last number will be 1/602. These are all the necessary numbers to get S1 that is greater to pi. In the second step, we calculated T1. T1 was the sum from S1, that's why we used S1 as a previous sum, plus the sum from n equals 1 up to m1 of q sub n. And this gave us m1 equals to 1, which made all the sense in the world because the first one was minus 1, the first negative number, and this number was 3.14 something, so 3.14 minus 1 is smaller to pi. So T1 was smaller to pi. Then in the third step, we got again a value for n1. We had that S2 was T1 as a previous sum, plus the sum from n equals n1 plus 1, in this case it would be 302. We actually set it to 603 because of the way the indexes were moving in the computer. And the result for n1 was 4,444. But again, in our case, it's not this number. It is going to be 2,222. And we are adding positive numbers. And now in the fourth step, we had T2, that it was S2 as a previous sum plus the sum from n equals to 2, because it was m1 plus 1, up to m2 of q sub n. And the value we got for m2 was 3. But again, the indexes in the computer, we have 1, 2, and 3. But for us, in the sequence q sub n, this is the first index, and this is the second index. So for us, m2 is not equal to 3, but it is equal to 2. And so our sequence ended up being v sub n. It was the first 301 positive numbers. So we have 1/2, 1/4, 1/6, and so on up to 1/602. Then we have the first negative number, because m1 was equal to 1, minus 1. Then the following numbers would be from 1/604, 1/606, up to 1/4444. And then we go back to the negative numbers, and we are only subtracting 1/3. And then again, a lot of positive numbers we can calculate, n3 and then m3. And this will be our sequence. And with this sequence, we have guaranteed that the series of p sub n will be equal to pi. Now, what's very important about this theorem is not that we can make this series converge to pi, which, by the way, the answer is yes, we can. What's important about it is that when we add numbers, we have the commutative law. We have that 1 plus 3 is equal to 3 plus 1. But what's impressive about this theorem is that for every real number, there is a way to reorder our sequence so that the new sum converges to this real number. So when we're working with infinite sums, then we don't have the commutative law. And that is something very important to remember.